Hello, everyone. I'm Weiran Liu. Today, I will present our work, OP-Boost, a vertical federated tree boosting framework based on auto-preserving desensitization. This is joint work with Xiaochen Li, Yuke Hu, Han Wenfeng, Li Peng, Yuan Hong, Hui Ren, and Zhan Qin. The presentation consists of three parts. The first part is about the introduction and the program definition. The second part is our key observation and our construction. The final part is about implementation and evaluation. So let's start with introduction and problem definition. What is a decision tree and grid tree boosting? The decision tree builds a branching model that close to the labels. For example, assume we have the following dataset with the features x1 as age and x2 as a retired, and the label as if the individual likes playing computer games. We can build a decision tree based on the dataset, showing that if age is less than 21, then the individual would probably like playing computer games. Furthermore, the gradient boosting decision tree trains many decision trees. The S tree is built based on the gradient information from previous I-1 trees. The final decision is the sum of all prediction results on each tree. For example, we can build a gradient boosting decision tree based on the same dataset containing two trees. The first tree is the same as the previous trained decision tree, and the second tree shows that if retired equals false, then the individual would probably like to play computer games. XGBoost stands for extreme gradient boosting. It is an optimized gradient boosting tree algorithm. It also refers to the library name that implements the XGBoost algorithm. The library is designed to be highly efficient, flexible, and portable. It supports distributed training, suitable for large datasets. In many scenarios, multiple parties holding different features of the same training samples would want to jointly train the model. Suppose credit company A wants to predicate credit rating. The model would be better at banks B and e-commerce company C's help. Let's assume that bank B, e-commerce company C, and credit company A all have some features for the same individuals with aligned IDs. Bank B knows their yearly expense and yearly income. E-commerce company C knows the shopping time per month. Credit company A knows auto insurance claims filed per year and their credit rating. If they can collaboratively do training, they would have a better model for predicting one's credit rating. However, there are some security and privacy problems with collaborative model training. These programs are not limited to the GPDT and XGBoost, but for all federated learnings. During training, each party is unwilling to directly share their private data to others due to security, privacy, or legal requirements. After training, the model itself will leak information about samples. There are some existing solutions, which can be categorized as cryptography-based solutions and privacy-based solutions. For cryptography-based solutions, we can use homomorphic encryption or multi-party computation techniques for secure training. The pros are that they can achieve provable security based on crypto assumptions, and there are many new optimizations on crypto techniques. The cons are that they involve huge computation and communication overhead. They are hard to implement and incompatible with existing systems. That is, we cannot do training using existing libraries in a black box manner directly. For privacy-based solutions, someone may use naive desensitization techniques such as rounding or generalization to desensitize data before sharing. However, such approaches do not have provable privacy guarantee. Others may discretize and add random noises to features while satisfying local privacy. So the pros are that they are straightforward to implement and compatible with existing systems. The cons is that it suffers from severe accuracy loss. We know that secure GPT training is a very active research area. We remark two new solutions. One is based on MPC and FHE accepted by the Usenix Security 2023, and one is based on the different privacy accepted by the CCS 2022. In this work, we propose a new framework, OP-Boost, for tree boosting algorithms satisfying distance-based LDP and vertical federated learning. Our framework doesn't require all parties online throughout the entire process. Also, our framework is compatible with existing systems. To support our framework, we introduce a new definition, probability order preserving desensitization with method, global map, adjust map, and local map. Global map achieves accuracy improvement compared to the LDP-based method. Adjust map and local map achieves the accuracy improvement compared to the DLDP-based method. We conduct comprehensive theoretical analysis for both privacy and utility with the new order preserving matrix weighted Condell. To demonstrate the effectiveness of OP-Boost, we have a comprehensive experimental evaluation on GBDT and XGBoost. We evaluate for various tasks, including range query, binary classification, multi-classification, and regression. For several aspects, including accuracy, communication, and computation overhead. OP-Boost has been open sourced. It is included in the project MPC4J, an efficient and easy to use MPC and DP library mainly written in Java. The source code is available at the module MPC4J SML OP-Boost. Here, let me show the key observation and our construction. We introduce a GBDT training procedure with an example. Suppose the current tree structure only contains a root node. Step 1 is to compute the first and the second gradient statistics GI and HI for each sample. Step 2 is to iterate all candidate split points and find the optimal split point and maximize gains shown here. We know that GBDT first needs to sort edges and other features before finding candidate split points. In the example, there are 4 candidate split points for edge, where the split condition is the average of its neighboring features. For example, 9 represents that split points are here, and 9 is the average of 6 and 12. Our key observation is that although the split condition is decided by the average of some feature values, all candidate split points are selected based only on the orders of the feature values. Following the key observation, we propose a new framework, OP-Boost. For other parties that do not contain the label, they map all feature values to a unified discrete data domain, desensitize the feature values by order preserving desensitization algorithms, and send them to party A, which has the label. Party A finds the best split points over the features to construct the trees, where the split conditions are computed using the averages of the order. Then it requires a specific desensitized feature values to other parties. Other parties replace all desensitized feature values with orders, and the response desensitized feature values of split points. Finally, party A obtains the complete tree model for predicating new samples. Now come to the question, can we construct order-preserving desensitization algorithms? So the first question is, can we construct absolute order-preserving desensitization algorithm while satisfying LDP? If you are familiar with cryptography, this relates to the definition of order-preserving encryption. However, order-preserving encryption is a deterministic scheme, and all differentially private algorithms should be randomized algorithms. It seems challenging to construct an absolute order-preserving desensitization algorithm with LDP guarantee. The next question is, can we construct a probability order-preserving desensitization algorithm while satisfying LDP? Recall that there is a variant of LDP definition named distance-based LDP, DLDP. A simple DLDP mechanism is to add Laplace noise, which the Laplace scale parameter b equals 1. The intuition is that if xi is less than xj, then after adding Laplace noise to get yi and yj, the only case that yi is greater than yj is that xi as a very large positive noise shown here, and xj as a very large negative noise. So in this figure, only here that can occur that yi is greater than yj. So from this situation, we can get that we can have that yi is less than yj with very high probability. Recall that in CCS 2022, Amrita et al. Introduced a notion of epsilon DLDP odor preserving encoding. Following this idea, we propose a new definition, probability odor preserving desensitization. Denote S as the sensitive sequence and Y as a noisy sequence output by a desensitization algorithm R, where yi equals Rxi. So algorithm R is probability odor preserving if for all I and j, if xi is greater than xj, then the probability of yi is greater than yj has a lower bound, gamma t. We propose 3 odor preserving desensitization algorithms: global map, adjust map, and local map. Global map is based on the exponential mechanism, where the scroll function is defined based on the distance between the input and the candidate output. In adjust map, we split the privacy budget epsilon into epsilon partition and epsilon neighboring, where we choose the output partition with epsilon partition DLDP and desensitize the value with epsilon neighboring DLDP. Local map is similar to adjust map, except that we set epsilon partition as infinity. The theorem shows that for local map, if x and x prime are in different partitions, then there's no permanency guarantee. Otherwise, we can obtain epsilon neighboring DLDP. Let me briefly show implementation details and evaluation. In our implementation, we noted that the complexity of exponential mechanism sampling is OD is inefficient when D is large. In such case, we use bounded discrete Laplace to do the sampling, obtaining O1 complexity. We proved that adding the noise sampling from the bounded discrete Laplace distribution satisfies 2 epsilon DLDP. We used weighted Kendall to measure how the output sequence is odor preserving. You can see that local map is the best. Here is the local map. Local map is the best, but with the drawback that there is no permanency guarantee when 2 inputs are in different partitions. Adjust map and the global map shown here are better than piecewise shown here, where piecewise is the state-of-the-art LDP mechanism for numerical values shown in ICDE 2019. The performance for the range query task also shows that our mechanism can achieve better accuracy. We do evaluations on binary classifications, multi-classifications, and regression tasks. We know that we also evaluate our framework on an industrial dataset that contains about 330,000 instances with 300 features. You can see that we need about 1 to 2 minutes to do the training, which is efficient even for such a large dataset. The source code is available at MPZ4J in the module MPZ4J SML OpBoost with many test cases. Please feel free to try and let me know if you met any problems. So that's it. Thanks for listening.